Hello, ma'am. Good morning.
Good morning, Professor.
Good morning. So we'll wait for another 2 minutes, or we can start now.
Okay, sure. I'll wait for another 2 minutes. Then we
Yes,
can
yes.
start.
The students are joining, so we'll wait for another 2 minutes. Then I'll introduce. Then you can start. So
Sure. Thank you.
at 10:03 exactly we can start. Fine. So what is the time now at Sri Lanka? I think 1 hour before.
It's exactly 10 o'clock.
10 o'clock, same time zone, na?
Yeah.
Okay, okay. So you are in office or at home?
I know today I stayed at home because I wanted to have this meeting, conduct this.
Okay, okay.
So, yeah, I'll be doing it from home.
So you are taking the classes of BTech there. Now you are, I think, not a researcher, means, not the position has
No,
been changed.
now
Senior lecturer.
I'm a senior lecturer, so I'm taking modules for the BSc honors engineering degree,
Okay,
but specializing in computer science and engineering. So
fine.
I'm under that department.
Okay, okay, good, good. So thank you for my accept my invitation for today's session also. Okay, so I think student has already joined, so we can start, huh? No problem. So let me
Okay, thank
introduce
you.
Dr. Aloka Fernando. I know her for the last 3 to 4 years. We are working together in many research paper also. So she is currently as a researcher and faculty at University of Moratuwa, Sri Lanka, um, and specializing in NLP, NMT, like your that is your neural machine translation, multilingual language models, and especially in low resource language technology. And as you know, Singali also coming under the low resource languages. So her research focus on developing innovative data augmentation and corpus mining techniques to improve this machine translation performance for low resource languages such as Sinhala and Tamil. So she has contributed significantly to the areas of parallel corpus creation during her PhD work, multilingual embedding, cross-lingual representation learning, and machine translation for low resource languages. Her work has been published in leading NLP and AI conferences and venues. So, advancing language technology for unrepresented language and promoting inclusive AI research. So, today, our talk title is Your Data Augmentation to Improve NMT for Low Research Languages. So, hope the session will be good. So, thank you, ma'am. Now, session is yours. You can share the screen and you can start. If any network issue, then you can, if required, you can off your video also, no problem. But you can continue. If net is good, then you can continue.
Right, sure. Okay, thank you very much, Professor, for the introduction. So let me share my screen first of all. Right. So I hope it's visible now to everyone.
Yes, yes, Aloka ma'am. Yes, video.
Okay, thank you very much for confirming. So today I'm going to talk about data augmentation to improve neural machine translation for low resource languages. So let's try to look at what is machine translation. So here in this presentation, I'm going to focus on text to text translation, right? So all of you are familiar with using Google Translate, right? And many more proprietary models have been emerged now, but basically we are going to focus today on text to text translation. That is, when a sentence is given in a source language, can be any language, can be Hindi, can be Sinhala, can be English. So the objective of the translation model is to translate it into a target language, right? So if we think how to train such a machine translation model, the popular translation models are neural network based, right? So therefore, we call this type of translation or training a neural network in order to learn the translation task, we term as neural machine translation, right? So there are few things which are essential in order to train such a model. So we need something called error data, right?
Aloka
So if
ma'am,
you,
Aloka ma'am,
sorry,
sorry to interrupt you. Ma'am, you can off your
yeah,
video. Means voice is cracking. You can off your video.
okay, sure.
Yes. Voice is little cracking. Yeah. Make it full screen. The slide is okay, but your voice is cracked. So that's why, yeah. Continue, ma'am. Make it full screen.
Okay, right. So I hope it's in full screen mode now.
Yes.
So, okay. So we were looking at the essential component to translate to train translation model, which is the parallel data, right? So if we need to train a model to translate from English to Sinhala, we need parallel data that is the same sentence in English and Sinhala both. Likewise, we need lot of data, right? So then the accuracy of these translation models will be high, and also the translations are reliable, right? So if we just take a look at the history, how these translation models have evolved. Very initial stages, it was rule-based, and then for like almost three decades, statistical machine translations were dominating the translation research. And towards mid 2010s, there was introduction to neural machine translation by means of RNNs, LSTMs, etc. And with the emerge of the transform architecture, now almost all the state-of-the-art translation on using the transform architecture, right? But they started as a sequence-to-sequence architecture where the encoder is also a transformer block and the decoder is also a transformer block, right? So if we take the performing models, right? So current models are mostly generative based, right? So that is only the decoder part of the sequence to sequence architecture, right? And some of the significant models have been GPT-3, Bloom, GPT-4, current models, and then we also have Google Translate. Google sorry, we have the Translate Gemma, which is from Google, and also we have Omnilingual Translate, which is by Meta, but the model has not been released yet. Right, so we see that generative models are also picking up, but it's a win-win situation when it comes to some of these lower source languages, which performs better the sequence to sequence or generative models. Right. Now, what is the difference when it comes to these languages? Because in the world there are more than 7,000 languages, right? So for all these languages, are these models performing equally well? Unfortunately, no, it's not the case. So languages, we can divide it into three categories: high resource, mid resource, and low resource. If we take the high resource languages, out of the 7,000 languages in the world, we have only very few languages, right? Which has data in millions and billions, right? And then we have the mid-resource languages, but unfortunately, majority of the long tail of languages, that is more than 6,000 languages, are under-resourced or low resource or very low, falling into the extremely low resource category, right? So we have so for these extremely low resource languages or low resource languages, the NMT perform the model performance, even when it comes to machine translation, is really poor, right? So let's see what are the reasons, right? So the main reason is limited or lack of data, lack of parallel data, the type of data we want to train NMT models, right? And the complexity of language. If you take single morphologically rich language, right? So words are inflected and grammar rules are not so straightforward. It's not simple, right? And then when it comes to other linguistic tools such as post taggers, named entity recognizers, that support is also very low, right? So therefore, it's in a very low resource setting that we are going to improve this neural machine translation for low resource languages, right? So out of these problems, the parallel data scarcity problem is the main culprit, right? So we see that for high resource languages such as English, German, French, right? So NMT models um, for the using the transformer architecture produce state-of-the-art results. But for if we train a translation model using the same transform architecture between English and Sinhala or English and Tamil or between Sinhala and Tamil, I'm actually using these languages because they fall into the that is mainly the languages which I've been researching on. But even in India, there are most of the languages, dialects, Urdu, those languages are very low resource languages, right? So when for these low resource languages using the same transform architecture, the results are suboptimal, right? So why is that? Right? So when the parallel data is less, the number of sequence to sequence, the sentence to sentence mappings are also very less. And in the parallel data set, the coverage of the vocabulary is also less. Therefore, the model during the training time does not recognize such words, right? And also, there are inadequate translation mappings or examples for the model to see and learn from, right? So therefore, when it comes to low resource languages, morphologically low resource languages such as Sinhala and Tamil, this the data scarcity problem will worsen the NMT performance, right? So now, how do we overcome, right? So there's a research domain called data augmentation. So under data augmentation, we look at how we synthetically generate this parallel data to train better NMT model, right? So according to Ranatunga and Costa Jausa et al., right? So they broadly categorize these data augmentation techniques into four types, right? So I mean, identifying or generating synthetic parallel sentences, right? So that means you take parallel sentences or translation pairs, and then you can try to change the words, change phrases, and generate translation. And then we have something called bytex mining. Again, I'm going to go into detail on this bytex mining task, so I will not. I will skip it. Skip the explanation part. So bytex mining is a very good low cost technique to mine for parallel corpora even at scale, right? So that how most of these low resource languages have given emphasis for this NMT research because of this bytex mining technique. Then we have the parallel data preparation, right? So we can generate data, parallel data synthetically or else using bytex mining techniques, but these may be noisy, right? So extracting high quality translation pairs from these uh, parallel data sets we call as the parallel data filtration or parallel data curation. And back translation is also a common method where we use monolingual data using a low performance translation model, try to generate the source side or the target side. Right, so in this research, now I'm going to share a research which was for the bytext mining. So let's understand what is bytext mining and how to improve the bytext mining task for this for a low resource language. Right, so the technique what I'm going to present can be adapted to any new language pair. Right. So what is bytext mining? Right. So we have parallel data. Right. So we have parallel data in the internet, in the PDFs, etc. Now, for example, if you take the Wikipedia website, same topic is available in English, Hindi, Sinhala, in multilingual language. Right. So if we extract the content and if we extract the content, definitely we can find translation pairs, right? So that's the idea. And not only the internet data, right? So there are government websites, right? So most of the time, when the government put out information, it has to be put out in all official language, right? So in Sri Lanka, there are three languages, official languages, Sinhala, English, and Tamil, right? And in India, maybe there are some number of official languages, right? So I'm not really sure the exact number, but they will put out the information in all these languages, right? So that is a very good source where we can identify in order to initiate the bytext mining process, right? So we identify and then crawl the web page, right? Then at the document level, we can align, right? Because it is like if we take the Wikipedia page, now let's say we take the page for, let's say, Olympic 2024, right? So 2024 Olympic page is in English, Sinhala, and Hindi also, all three languages, right? So we have to first figure out what web pages are having this translation content, right? So then that is called document align, right? So once the documents are aligned or the parallel documents are identified, then we can go inside the document, check the sentences and see what are really mapping, translation pairs, right? So that is called sentence align, right? So let's suppose the English document is economy report and the Sinhala document is Arthika Varta, right? So in this economy report, there will be like 100 sentences, and in the Sinhala document, there are 150 sentences. Then in the sentence alignment task, we see how many are now having translation overlaps and how many can be taken as parallel data. Then the 100, 150 we compare and maybe we identify like 75 sentences. Then we perform another additional task called the curation task, the parallel data filtration, where they might be, let's say, those sentences are very short. For example, or else sometimes they are only mostly numbers. So we can filter out some of these less informative sentences and we can curate the data and finally we can obtain a parallel corpus for a given language pair, right? So overall at a high level, that is the now, how do we perform the document alignment? How do we perform the sentence alignment? That is the research part we have to focus. Now, in order to now we are expecting a computer to do this, right? So we are feeding the in our example the 100 sentences in the English document and 150 sentences in the Sinhala document. We are giving to the computer and asking the computer to do some computation and identify what are translation pairs, right? So, but the computers don't understand the language. They don't understand the sentence meanings. What they understand and good at will be numerical calculations and comparison, right? So therefore, what we do is we need to convert each and every sentence into a representation, a numerical vector representation, right? So how we do this, right? So there are these encoder models which have been trained and released, right? So these encoder models, what they do is they get a sentence or a paragraph and they give out a numerical representation by means of a contextual embedding for that particular sentence or the paragraph, right? So in order to get this contextual embeddings, we use something called an encoder model, right? So these encoder models have a drawback, right? Now, as I said before, not only the low resource languages lacks parallel data, but the tools using to generate more data is also not performing well, right? So this is now we have another limitation with the encoder models that um, convert it into numerical representation, right? Now, the motivation of this, we have this multilingual embedding model. So, what it should do is if there's a sentence in English and Hindi, right, in the embedding space, the representation should be very close because these two are translation pairs, right? But in reality, it's not the case, right? Now, we want it here, right? This same sentence is available in multiple language, right? And we want everything to be in the same proximity. But in reality, they are somewhere lying, right? They are far apart. So as a result, dissimilar sentences which are not translation pairs can be closely represented in the embedding space. Therefore, that's why this bytex mining or this para sentences which are coming out may be noisy as well, right? So why does this happen? In these encoder models, one thing is it's trained with mostly monolingual data, right? So when the only data it is trained is monolingual data, right? So it doesn't know really how to do the alignment in the embedding space, right? So another way to overcome this is using a cross-lingual embedding or cross-lingual objective. And we see that these monolingual data trained models don't have a cross-lingual objective either, right? So as a result, right, because the model is training to give a representation only. It has not been specifically trained to position the embeddings uh, as close as possible, right? So, for example, you take the English sentence and the Hindi sentence, they are far apart when it should be close as possible. So, in this research, what we have done is we have done an alignment of this embedding space so that the English sentence and the Sinhala and Tamil sentences will be in close proximity for the translation pairs, right? So that is the objective of this work, right? So In literature, we see that in order to train these encoder models, starting from the bird training objective, they mainly use mass language modeling, right? So mass language modeling is a pre-trained objective where certain tokens are masked, and during the pre-training stage, the model is trained to predict these words, right? And there are variants as well, right? Subword masking, in subword masking, a token will be masked. In whole word masking, entire tokens in the words will be masked. And then there's another masking variant called entity or phrase masking, where they only mask the consecutive words in a entity or a phrase. And we have also span masking, where randomly, let's say, identify two or three words in a sentence and mask all the tokens in particular sentence span, right? So, but this masking strategy have only been applied for the monolingual data, right? But alternatively, now the work of Lampel and Cornell have proposed that applied masking to concatenated parallel data can now improve cross-lingual representation, right? So with this motivation, in this mass language modeling objective into the parallel sentences in that direction. Taking that as the direction, we have proposed linguistic entity masking as a continual pre-training strategy to improve cross-lingual embedding. Right. So we have encoder module which is already trained to produce some kind of entity. So with linguistic entity masking, now we are going to do a alignment between the two languages to to facilitate the byte explaining task. Right. So in a graphical manner, we are representing our masking strategy. Len mono means when the linguistic entity masking is applied to a monolingual or in monolingual data, right? So only one language is considered there at a time, right? So if we are training for English Sinhala pair, right? So first the English sentences will be masked and then Sinhala sentences will be masked, right? And these are the other variants of mass language model. So how do we apply that to the parallel data? So we take the parallel sentence, we use existing parallel sentences for this, right? So we concatenate it, right? So we concatenate it and then identify tokens for masking, right? So we conduct, we do a continual pre-training on an existing encoder using the LEM-mono, that is applied the mask language model, linguistic entity masking for the monolingual data, and then further we continually pre-train using the concatenated parallel data as well. Right. So let's look at the assumption. Now I said the masking strategy is linguistic entity masking, right? So as linguistic entities, we mainly identify named entities, nouns, and verbs, right? So those are the specific type of words which we select to mask. Whereas in the other masking strategies like whole word masking, subword masking, span masking, they have identified these tokens or words to mask in a random manner. So we are being specific only for linguistic entities. So why we consider linguistic entity? So this is the attention matrix uh, for for the English sentence and a single sentence. Now you can see most of the time the token is having the highest attention in a sentence or highest self-attention in a sentence are mainly nouns or verbs, right? So nouns or verbs, therefore nouns, verbs, there's no name, there's a name entity, but mainly these are the type of words which will get the highest self-attention. So therefore, we target those tokens for masking. Then, now in our strategy in the linguistic entity masking, we only uh, mask a single token, not a consecutive span. Right? So why we do that is because this for list of languages, tokenizing step predicts more tokens. So if we keep on masking consecutive words, it is going to weaken the context for the model to predict the words properly, right? So therefore, instead of masking a span of tokens, we only mask a single token which is selected, uh, which is belonging to a linguistic entity. Then, how do we train? Right? So this is our training strategy. We start with a multilingual pre-trained model, right? Because our objective is to improve the alignment or the language learning has happened in a multilingual pre-trained model. Then, in the first continual pre-training step, we apply the linguistic entity masking for the source side and target side, and then we conduct the first continual pre-training step, which we call as LEM mono, right? Linguistic entity masking applied for monolingual set. Then, as shown in the previous slide, we concatenate the parallel sentences and then we keep on masking. So this will result in LEM para, right? So now this is the final model is what we are interested, right? So this is an improved encoder. How is the improvement happen? It has improved so that for transition pairs, the encoder will return embeddings in close proximity, right? So that's the improvement we are expecting. Right. So this is the theoretical framework, right? So for LEM mono, we select a monolingual sentence, then we identify the linguistic entities, right? So some may be verbs, nouns, named entities, etc. Then we select 15% of tokens from until we mask a total of 15% from the entire sequence length, right? So, for example, if this 4, 5, 6 uh, is maybe a, let's say, a verb, right? So in this we select one token and we mask it, right? So likewise, from each linguistic entity, we identify a token for masking until it reaches 15% of the total sequence length. So the pre-trained objective is to minimize the cross-entropy loss or the token prediction loss. So same thing is applied into the parallel data. So in this concatenated parallel sentence, the token is each token from a linguistic entity is masked, right? So in a parallel data, we follow the intuition such that in order to predict the token, not only it will benefit by the context in the same language, but also from its translation equivalent, right? So that is the same intuition which was followed by Corneo and Lamper. So here again in the spiral sentence, we pre-train during the second continual pre-training step, we minimize the cross entropy loss or the token prediction loss, right? So uh, that is basically what the theoretical framework behind a linguistic entity masking strategy, right? So we can. So now I will explain the experimental setup, how we actually did this model training. So, okay. So we have taken this study directed at language pairs between English Sinhala, English Tamil, and Sinhala Tamil. So why we have selected these three languages? Because these three uh, are the official languages in Sri Lanka, right? So as the pre-trained model, we have used XLMR model, right? So XLMR model is actually a it's actually a multilingual model, encoder model, which is trained on 100 languages to return a vector representation of the given sentence. Right. So, in order to implement the linguistic entity masking, I have customized the implementation of the sentence transformers library so that uh, the masking will be only limited for linguistic. And the continual pre-training has been done on GPU or NVIDIA Quadro RTX 6000 GPUs with 24 GB VRAM. Right. And then evaluate. How did we evaluate? Right. So the improved encoders should be improving the sentence alignment task. That is identifying uh, the parallel sentence. Right. So that is the intrinsic evaluation. And as extrinsic evaluation, we have used the parallel data filtration task. Right. So in parallel data filtration or parallel data curation task, we already have parallel sentences identified, right? But not all those parallel sentences are clean. They are of good quality, right? So therefore, we need to calculate the translation score, right? Which we calculate by taking the by calculating the cosine similarity between the two sentences. So that is extrinsic evaluation. Right. So now let's look at the results. So experiments. So in this particular experiment, here we are trying to analyze the how the existing masking strategies perform, right? For a sentence alignment task. So sentence alignment we already discussed. It is the task of identifying translation pairs given monolingual sentence, right? So here I'm presenting the results for these three directions. So here we have English some number of sentences and Sinhala some number of sentences, right? And then we identify how many parallel sentences have been identified on a human annotated data set. Right? So as masking strategies, right? So because now we are improving the linguistic entity masking, so there should be a need for such a masking strategy. The existing masking strategies are performing already better, then uh, then it's a question mark as to why we need to improve, right? So we actually do an empirical study to see whether these have the potential of these existing masking strategies have the potential of improving the sentence alignment task, right? So we take the embeddings from uh, from uh, so what we do is we take the XLMR model and we do a first step continual pre-training using these masking strategies. And then we take the encoder, get the embeddings and do the sentence alignment task. So now what do we see? So we see that now this blue color bar is the embeddings taken from XLMR model. And you can see the rest of the bars are actually less. There's a slight variation for the green colored one for the Sita direction, Sinhala Tamil direction. But in general, for the other two languages, it's performing very less. Right? Now you can say, so what is the outcome? So the outcome is this other masking strategies in general are actually decreasing the sentence alignment task performance, right? So that means the other masking strategies are less helpful in order to improve the sentence alignment task, right? So that is also obvious based on the results, right? So then for XLMR embedding, these are not improving the embeddings, but actually it is actually degrading the embedding quality. So therefore, we have to introduce, that's why we have introduced the linguistic entity mask. So now we in this situation, so we have improved the encoder using the LEM monostep, the LEM parastep, and then we have evaluated on the sentence alignment task. And we see that always the LEM para is going to improve the final task performance for English Sinhala, for English Tamil, and Sinhala Tamil diction, right? So this is the summary, right? So earlier they were the empirical results tables, but now let's look at the summary. Now what is this blue color, right? So this blue color one is the improved encoder versus XLMR base without improving anything. Now, compared to the baseline XLMR return embeddings, now we see that the improved encoder return embeddings and the performance, as a result, the performance of the sentence alignment task is actually far more better. It has produced gains. Gains are positive. Then what is this orange color bar? So this orange color bar, now this is the initial work of Lampel and Cornell, right? So they have also used the same thing, MLM and TLM, mass language modeling on monolingual data, mass language modeling on parallel data. In their case, they have only considered random token masking. Now we can say that our technique, we have masked linguistic entities, they have masked uh, random tokens. So, which means masking linguistic entities is going to give a performance improvement. If you see, like for English Tamil, this has drastically improved. And similar for Sinhala Tamil and English Sinhala as well, right? So all gains are positive. That means the linguistic entity masking is going to help improve the embedding alignment for low resource languages, and as a result, the aligned sentences are now of better quality, right? So that is the takeaway from this particular slide. Then we said we have conducted the study uh, for another task, which is parallel data filtration. So in parallel data filtration, we already have the sentence pairs in Sinhala in the two languages. So what we do is we take the encoder models, get the representations, and calculate the cosine similarity and see the translation score. Then we take the translation, the sentence pairs having the highest translation score, and we train NMT models and compare the results. So we do this using two parallel corpora. So first one is the NLLB corpus. Second one is this CC aligned corpus, right? So these have been all these two corpora have been generated by using the bytext mining strategy, but they have used some different but they have used different encoders in order to do it. Right now, what we are doing here is we are going to recalculate the translation, the scores, and we are going to identify 100,000 topmost quality language translation pairs, and we are going to train NMT model. So now let's look at the result outcome. So XLMR, black color is we take the XLMR encoder, identify the top 100,000 train NMT models. Right, okay. So that means it has performed the least. Right now, whatever the corpora, CCLI or CC NLLB, it is the same. Then we improve the XLMR with MLM and TLM. This is the Lampel and uh, Corneo improve, right? So now we can see when the XLMR is improved using the random token masking, it has managed to give a improvement compared to the XLMR. Then we use our strategy, right? We take our linguistic entity masking and improve the XLMR model, get the embeddings, calculate and identify the top quality 100,000 para sentence. That is the orange bar. So this orange bar has performed slightly better uh, than the XLM, the Lampel and Coneo work of them, right? So it's safe for us to say that these improved encoders are performing better even when it comes to the parallel data curation task, right? So this is another evaluation which we have done to prove the strength of the linguistic entity masking. Right. So the contributions of this research. So firstly, our empirical study shows that the existing masking strategies are less likely or less favorable for sentence alignment tasks. So as a result, we introduce linguistic entity masking. Then we see that the linguistic entity masking is giving a significant improvement for the Sinhala Tamil language pair and uh, Sinhala Tamil language pair compared to other two, right? So other two also perform well, but this is the best gain we have got. And then we can see that even for the other two language pairs, it's around 1.7 and 2.4, which is also coming close, right? And finally, we have done an ablation study, another set of ablation studies to find out what is the most impactful linguistic entity which actually contributes to improving the representations. And we found that it is mostly when named entities and verbs are masked. So, compared to nouns, when these two are masked, they contribute towards better performance. And you can find more details. This is an open access paper which is published in Knowledge and Information Systems Journal. Right, so the title of the paper is Linguistic Entity Masking to Improve Cross-Lingual Sentence Retrieval Capabilities of Multilingual Language Models. Right, we have proven that this linguistic entity masking is actually performing well for English Sinhala, English Tamil, and Sinhala Tamil language pairs, three language pairs. So it therefore, it should also improve the performance of other, in general, for other low resource languages as well. Yeah, so that is what I had to present. So, what in this study, what we have done is improved existing encoder models so that they return reliable embedding to improve the sentence alignment task, right? So as a result, the resulting parallel sentences will be of high quality, right? So that way we can now introduce more parallel sentences to a language pair. All what we have to do is identify sources, maybe from the internet, or it might be textbooks, or it might be government search documents, right? So which has translated content or content, and based on the sources, we can keep on parallel sentences and contribute to improve addressing the scarcity problem for that particular language. So, in terms of presentation, that is all what I have to explain. So, I will now do a hands-on session as well. So, before I move on to that, I'm ready to take up any questions. If there were slides which are not clear or you want to know more details, you may put it in the chat or else Anu can ask. And I can pick up some questions before I move on to the next
Yes,
one.
anyone having any questions, you can unmute. Yes, Gunis, yes. Yes, you can unmute. You can unmute and ask the questions. So, ma'am has done the work for the Tamil and Sinhala. So, if in your language you apply to this NMT, so any kind of queries are there from your side, you can. You can unmute yourself and ask the question. Otherwise, ma'am will go for that. I think my ma'am demo, na, that Hanson will be there.
Yeah, I have a demo.
So anyone having any questions, you can unmute. Once again, I'm telling, you can unmute and you can ask the question. Okay. Yes, Arkavarta, have you any questions?
Hello, Dr. Satyaranjan.
Yes, Arka. Yeah.
No, I don't have any questions. I will drop a mail if I have any thing to ask.
Okay, okay. Good, good.
Thank you.
I can share my email
Yes,
address
yes.
in
Yeah,
the chat.
yeah.
Yes. So you can direct any questions to me.
Yes, ma'am. You can go for the demo.
Okay. So I'm actually continuously working on the data augmentation side now, targeting the generative models. So if anyone is working on such a similar task, you might want to, there's anything you would like to know about the ongoing work, you can contact me, or for even for collaborations, you can contact. Okay, I'll now start demonstrating the hands-on session. Right. So I hope this is visible. Right. So here now what I have done is I'm now going to demonstrate the sentence alignment task. Right. So we discussed about it in the presentation. So sentence alignment is given there are sentences in monolingual language, right? We try to find what are actually equivalent translation pairs, right? So here I have taken some sentences, right? So I have taken 5 English sentences and translations of them, 5 Sinhala sentences, right? So they are now in correct order, right? So hello, how are you? The first sentence is ආයුබෝවන් ඔබට කොහොමද? Right? So likewise, now they are in order. So first sentence in English is a translation of the first sentence in Sinhala. Now, we are doing the task of identifying the translation pairs. Now, in the second step, now I'm going to shuffle it, right? So I'll shuffle the sentences. Right. So now you're not having the same, yeah. So that's cell number 1. And cell number 2, I'm going to show the sentences. So now the first sentence and in English is not really the translation of the first sentence in Sinhala. Right. So now we have 5 sentences in each language. So in the next step, what we are going to do is, right, so we are going to make use of a embedding model, right? So we are going to make use of an embedding model, and then we are going to get the embeddings for each of these sentences, right? So in order to get the embeddings, I'm going to use a model called XLMR Roberta. This is the same model, the base model, XLMR base model, which I have used for the linguistic entity masking task as well, strategy as well. So this XLMR Roberta is only, as I said, it's trained for 100 languages and it's using a massive amount of data for training. And in addition to that, so it's a Facebook released model. There are different versions. There are, depending on the model size, there are variants. So I have taken the smallest model, which is XLMR base, which is having 12 layers. Then we have XLMR large and XLMR XL. So that, sorry,
I don't understand. Saktan.
can you repeat the question,
Hello,
please?
just repeat the question. I don't think any questions are there. Hey, ma'am, continue.
Okay. So now this model is available in the Hugging Face. Now, if you take the Hugging Face, I think most of you all have been using the Hugging Face for models and datasets, right? So, in addition to XLMR model, there are other models as well which you can use. So, we are going to access this using the sentence transformer library, right? So, transform is the base library to work with Hugging Face models, right? So sentence transformer library is used for efficient for semantic search, right? Now this is a toy example where I'm targeting only five sentences, but in reality, it might be that we have 1,000 on one side, another 1,000 on the other side, or else 1 million on one side, 2 million on the other side. So it can be massive as well. So for efficient semantic search, we can use this sentence transformer library. And also, I have used several other libraries mainly for visualization, right? So maybe I can use this, I can share the collab notebook, but please don't run using this notebook. You can actually take a copy and maybe try this out.
You can share the link. I will share. Yeah, yeah. Ma'am
I
has
will
already
share.
shared.
I have shared it in the chat. So
Okay.
now everyone should have access, right? So you can take a copy and save this notebook into your own shared drive, on Google Drive, right? So those are libraries I have used. So the purpose of libraries is to read the encoder to get the embed and also for visualization. Right. So once you have installed the libraries, now you can import them, right? So from sentence transformers, you import sentence transform library, and that is the library which we are going to use to read the uh, model, right? Load the model. So since I have already done this, it has automatically downloaded, but it's like otherwise it might take some time depending on your network connectivity. Then what we have is we have an encoding step, right? So we take the English sentences separately and we get 5 vectors for the 5 sentences. We pass the Sinhala sentences separately and we get 5 vectors for the 5 sentences, right? So each vector returned by the XLMR model is having a dimension of 768 dimensions, and 5 means the 5 sentences we have. Then we calculate the cosine similarity, right? So I can erase it if I don't have the Sinhala rendered properly. So, but this is good enough to explain what happens, right? So now we have the English sentences, the 5 sentences, and then the embeddings we have already extracted. Then we have the Sinhala 5 sentences. Those 5 also we have the embedding. So we have a 5 by 5 matrix because with each and every sentence, now we are calculating the cosine similarity, right? So, for example, she loves to read books. So, with this English sentence return embedding, we get that embedding, and between the embedding of that and the first Sinhala sentence, we calculate the similarity. And the second, we take the same sentence embedding with the second Sinhala sentence, we calculate the similarity. Right? So this is actually going into 4 decimal places, but since it is rounded, all are 0.99. But when you calculate to 4 decimal or more decimal places, you get actually a difference. Right? So then you can identify the 2 sentences having the highest similarity. So based on that, now if you take this one, what is your favorite color? Right? So what is your favorite color? One particular sentence is giving one itself. That means the embeddings have actually been very much close for the 2 sentences. So therefore, it's returning one. So we can pick the translation pair as the fourth English sentence for the fourth English sentence, that and the particular sentence. Yeah. So based on the highest score, now we can find out what are the translation pairs, right? So you can view the score and the equivalent translation of it, right? So likewise, this two will be identified by the model as the translation equivalent. Right? But when you do that, now there might be some instances where it has not identified uh, certain pairs correctly, right? So, for example, this second one, it has not identified correctly, right? So that is why we need a parallel data curation task, right? Because this XLMR model, as I said, for certain sentences, though it is showing very high similarity, sometimes that is not the best, or else these similarity values were very close, such that there was only a small difference between the correct one and the wrong one, and for some reason the calculation is giving a better value, right? So these are the real problems we have when it comes to identifying these translation pairs. So that's why we recommend the parallel data curation step coming after this. So this is basically demonstration of the sentence alignment task. How we do that is pretty much is by getting the embeddings or representations uh, for each and every set. So here I have used the XLMR base model, right? So if you have improved, if now I instead of I can also use linguistic entity masking improve encoder here, right? So then now if the XLMR model identified, let's say, 4 out of 5 sentences correctly, an improved encoder model will let you identify all 5 out of 5 sentences. Right? So that way we can we use change in the encoder can change the translation pairs it has identified. Right? So that's a short demonstration of the sentence alignment task. So if there are any questions, I can answer, but you may take a copy and use your own 5 sentences in English and Hindi, or English and Urdu, or English and Tamil, and can try to experiment by your side, by yourself. Okay, right. So
Ma'am, for our model to consider working correctly, how much we should predict accuracy or precision should we take? Like here, where similarity is 0.99. So if something is wrong and still it is giving a high similarity, so how to tackle that part? That I did not
yeah,
understand.
so maybe this model, so we can do some evaluation and find out what is the best model working for our language. And maybe instead of XLMR, there's another language model called Laser, and we have also LabSay as alternatives. So laser models are now performing better. That was released actually after this work was taken place. So those will actually give you much more reliable scores to for correct translation pairs. So maybe we can look at the quality of the first 100 and evaluate, and based on that pick a proper encoder model for the task, or else go for different calculations, similarity matrices as well, right? So we have the cosine similarity, then we also have an improved cosine similarity calculation as well, right? So that works on a nearest neighbor basis. So that is much more reliable than cosine similarity. So we can use, there are other researchers which has tried to improve this similarity score calculation as well. So we can choose a different metric to calculate the similarity also. So these two combinations will actually decide the quality of the resulting parallel data. So I think that's a very good question you have asked. Thank you very much for that question.
Okay, ma'am, thank you.
I can take few more questions because I think.
Any other questions? You can unmute and you can ask if any questions are there. Yes, Annapurna, Sayandini. Okay, I don't think so. So let them.
Okay, so.
Any student from Africa continent? If you have any questions, Usman. I don't think so. Okay, ma'am. I think no questions are there. So if anything is there, they can mail you and they can also contact to me. And you have already shared that link so that they can go through and try to implement those things, even if required in their language also. So thank you again, ma'am, having another session tomorrow. So that will be on AI agents and agentic AI for NLP applications. So that is related to the workshop. So I think everyone will join again tomorrow. We'll meet again. Thank you, ma'am. Thank you very
Okay,
much.
thank you very much,
Nice.
audience, and thank you very much, Professor. Have a nice day.
Thank you. Thank you.
Bye.
Bye. So we have the next session at 12 o'clock by Dr. Naveen Saini from IIIT Allahabad. So he's going to give a talk on topic LLM assisted multi-objective prompt learning for low resource language summarization. So I have already asked him to give some hands-on also. Let us see. Thank you very much. Next we'll again join at 12 o'clock.